chapter 8 is where we get into what really is, finally, the crux of chemistry, where we're talking about quantities in chemical reactions, not just different types of chemical reactions, but how can you actually use these to calculate things. In particular, right, if you put in a certain number of reactants, certain amount, usually a mass, how much are you going to get out? How much could you possibly get out? How much of each thing do you need to make a certain amount of a product? And that's the question that's being answered here. So it's going to draw on nomenclature, because you have to know what the compounds are to either write out the chemical reaction. And it's going to draw a lot on the idea of a mole and molar mass, which is right, the numbers on the bottom of these periodic tables. That's how much 1 mole of those type of atoms weighs. And so we're going to be using that a lot. The analogy, though, that we're going to start out with is making pancakes. Because the concept here, in terms of figuring out how many pancakes you can make, is the same for stoichiometry, which is this process of calculating how much of, well, calculating quantities in chemical reactions. So stoichiometry or chemical reactions are recipes, and your ingredients are the reactants, the things that you're making are the products, just like if you're making pancakes. And of course, this is a simplified recipe. It doesn't have like oil or water or other things that you might need. But the idea is the same. So if you have 1 cup of flour, 2 eggs, and a half a teaspoon of baking powder, you can make 5 pancakes. Right? These are the amounts of things that go in, and exactly the amounts of things that go in. Right? You don't want to add more flour than 1 cup or less than 1 cup of flour, because then you're not going to get very good pancakes out of that recipe. So these are our reactants, and this would be our, in this case, single product. All right, so kind of a synthesis reaction. So the way this works, right, is if we have 2 eggs and enough of everything else, we can make 5 pancakes, usually flour and baking powder, things you're going to have enough of. But we can also use this to write a conversion factor or ratio between the number of eggs that go into a recipe and the number of pancakes that will come out. So assuming that we have an unlimited supply of flour and baking powder, for every 2 eggs, we can make 5 pancakes. So if we have 2 eggs, 5 pancakes, 4 eggs, 10 pancakes, right, so on and so forth, you can do the math and figure out how many eggs it's going to take to make however many pancakes. But they're always going to be in, well, for the pancake recipe, it's always going to be whole numbers of eggs. Right, so if we have 8 eggs, right, 8 eggs, and assuming, again, unlimited flour, unlimited baking powder, we can make 20 pancakes. And then one of the questions that we're going to also, one of the concepts that we're also going to cover in this is, what if you don't have infinite amounts of everything else? Right? What if we have limited amounts of flour and baking powder? I guess we're going to come back to that. But right, so if we have 8 eggs, but we didn't have enough flour, then we would be limited by the amount of flour that we have, and we'd have to look at that instead to figure out how many pancakes we could make. So we'll plant that seed for later. This idea, though, of the ratios like between ingredients and between the amounts of products that we can make applies to these chemical reactions. And the ratio, whereas in the pancake recipe, right, we have units of eggs, pancakes, or in this case, cups of flour or teaspoons of baking powder. Look at that is on the screen. Here we're talking about numbers of individual atoms. And usually we use moles because it's a lot more convenient to talk about these reactions in terms of moles. So we can write mole ratios between hydrogen and nitrogen or ammonia or we could write a ratio between nitrogen and ammonia. And for any of these combinations, we can write a ratio. So for 3 moles of hydrogen, how many moles of nitrogen would we need? How many moles of nitrogen do we need? Yeah, just 1. So this one's a little bit trickier because the 1 is there, but it's not written because we leave those 1s out. So if we have, again, so that would be a ratio of, right, if we put in 3 moles of hydrogen, we're going to need 1 mole of nitrogen to make 2 moles of ammonia. Just like if we went back up here to our pancake recipe, if we have 2 eggs, we're going to need at least 1 cup of flour to make 5 pancakes. All right, so we can do that ratio between each of the reactants. So if we had 3 moles of hydrogen again, that's required. How many moles of ammonia could we make? 2. So for these mole ratios, again, we're just looking at these initial coefficients. That's what's determining the ratio. And we could even do for 1 mole of N2, how many moles of ammonia could we make? Yep, just 2 again. So 2 moles of NH3. And those are really all the possible combinations, because we could write down 2 moles of ammonia first and then say how many moles of hydrogen would we need, but that's the same as this second ratio here. And we could say, oh, if we have 1 mole of nitrogen, how many moles of hydrogen do we need? But that's going to be the same as this ratio, just written the other way, which means the same thing. So these mole ratios are what we're going to be using to convert from moles of one thing in a chemical reaction to moles of another thing in a chemical reaction. Okay, so if we have 3 moles of nitrogen, I guess I don't need to write the of, 3 moles nitrogen, and again, assume an infinite amount of hydrogen, how much ammonia can we make, the NH3 over here? So for every 1 mole of ammonia, if we have enough hydrogen, we'll make 2 moles of, for every 1 mole of nitrogen, we can make 2 moles of ammonia. So we can use the ratio, right, so every 1 mole of N2 will give us 2 moles NH3. And we can use that as a conversion factor. Say 3 moles of N2, and just like or actually, let me write it this way. Just like our other conversion factors, we want to cancel out that unit moles of nitrogen. So we put 1 mole of nitrogen on the bottom. And then on the top, we put 2 moles of ammonia. And so that will make 6 moles of NH3. So we can also ask this question a different way. And in a sense, asking this question kind of in reverse, not quite. But how many moles of nitrogen, so how many moles of N2 are needed to completely react with 7.13 moles of H2, hydrogen. We can set up another conversion factor. What's the ratio between hydrogen and nitrogen? Anybody else? So if we have hydrogen, nitrogen, what's the ratio between those? 1 mole of nitrogen to 3 moles of hydrogen. So we can write that out. We can say 1 mole nitrogen, 3 moles, oh, that's a 2, hydrogen. So remember how I said unit conversions? It's going to be part of everything. Here it is again. So we'll put our 3 moles hydrogen on the bottom and 1 mole nitrogen on top. So now the question that's being asked with respect to this equation is, if we have 7.13 moles of hydrogen, how many moles of nitrogen do we need to completely react, right? So we're trying to figure out how many of those combine. And so you're going to take our 7.13 divided by 3, and we'll get 2.38 moles of N2. And again, our units here cancel and get replaced by moles of nitrogen. Everybody tracking so far? Pretty good? Some nods? All right. So get another reaction here. If we have hydrogen, which reacts explosively with oxygen to form 2 moles of water, how many moles of H2O result from the complete reaction of 24.6 moles of oxygen? And we're going to assume that there's more than enough hydrogen. Okay, so what are we given? Moles of oxygen. Oh, yeah. We're given moles of oxygen, so 24.6 moles of O2. And what are we looking for? Moles of we're assuming that there's more than enough hydrogen present. So we've got unlimited hydrogen here. So the question is, how many moles of water? So H2O. So we start with our 24.6 moles of O2. And in all of these problems, it's going to be taking the number of moles that you have, or sometimes you first have to calculate the number of moles, and then figuring out the ratio between what you have and what you're looking for from your balanced chemical equation, and then setting up a unit conversion problem, unit analysis problem. So we have moles of oxygen, and we want moles of water. So what's the ratio between oxygen and water? 1 to 2. So 1 mole O2 is 2 moles H2O. So if I add 1 mole O2 to the denominator and 2 moles of H2O to the numerator, then moles of oxygen will cancel, leaving us with moles of water. And so we're going to get 24.6 times 2, or 49.2 moles of water. It's a lot of water. So figure out what you have, figure out what you need to find, then find the ratio between those two things in your balanced chemical reaction or chemical equation. Okay, so this is going to be the core of basically everything we do with stoichiometry. It's going from moles to moles. I'm going to add another layer of complexity, though, because it's not going to be that simple, because we can't measure things, moles of things directly. We can only measure the mass. Or at least this point, we've only talked about measuring the mass. So our chemical equation contains conversion factors between moles of reactants and moles of products. So if we want to figure out how we get from one chemical to another in a chemical equation, we have to be in units of moles. But like I said, most of the time, we don't have the number of moles directly, we just have the number of grams. So we'll start with the mass of A, and then we'll convert that into moles by using the molar mass of A. Then once we have moles of A, we can take the ratio from the balanced chemical equation, that's what we did in the past few problems, and convert it into moles of B. And then from there, use the molar mass of B to convert it into the mass of B. So all of these problems are going to have this same structure. The work that you need to do is to figure out the molar mass and the ratio between the two different compounds. And those are going to be different pretty much every time. Or you'll have to calculate them. So what mass of carbon dioxide is emitted by an automobile when 5.0 times 10 to the 2 grams of pure octane is burned? Octane is one of the components of gasoline. So this is, by the way, this is octane. Okay, so what are we given? Yeah, 5.0 times 10 to the 2 grams. Oh, sorry. Oh, you said octane. Yeah. Yes, octane. And we're looking for yep. And not just moles of CO2, but it says what mass. So mass is going to be in grams. Because this says mass, that's grams of carbon dioxide. So we're going to find grams of CO2. Alrighty, so we're going to start our problem out here with what we're given. I'm going to change this. This is octane C8H18. So our general thing, I'm actually going to write this on the board. So we're going to have terrible dry markers. So we got grams of A. We need to convert that into moles of A. Then we convert that into moles of B. Then we convert that into grams of B. So A being what we're given, B being what we're trying to find. All right, so how do we convert from grams of A to moles of A? Magical ratio on the periodic table.
Find the molar mass of octane.
Molar mass, yeah. We'll have to use the molar mass to convert grams into moles. So our molar mass of octane is going to be the sum of all of the atoms that make up octane. And we can calculate that over on the side here. So we've got carbon, and we've got hydrogen. And we have 8 carbon atoms, and we have 18 hydrogen atoms. Carbon is, and so we'll multiply the number of carbon atoms by 12.01, which is the molar mass. And molar mass is in grams per mole. And the molar mass of hydrogen is 1.01. So 8 times 12.01, that's going to be 96.08. And then 18 times 1.01 is going to be 18.18. And then we add those two together for a total mass, I'll write it like this, of 114.26 grams per mole. So molar mass is inherently a conversion factor between moles and grams of a substance. So I said that this conversion factor, you either need to look it up on the periodic table because you've got just an element by itself, or you need to calculate it based on all of the different types of atoms. So it's not always going to be the same conversion factor, and in fact, most of the time, not going to be the same. But you can calculate it. You can always calculate it. You'll always have a periodic table on exams or in here. Alrighty, so 114 grams per mole. So we're going to put this is going to be 114.26 grams of octane. And that is equal to 1 mole of octane. Cool. So now we've converted from grams of A to moles of A. Because our units here, grams of octane cancels out with grams of octane. So now we can move on to the next step, going from moles of A to moles of B. So what is the ratio between octane and carbon dioxide? It's the 2 to 16. Yes, thank you. So it's 2 moles of octane to 16 moles of CO2. So where do I put 2 moles of octane? Is it on the bottom or the top? We want to get rid of moles of octane on the bottom. Yeah. So 2 moles of octane on the bottom, 16 moles of CO2 on top. And I know we did unit conversions before. There are some cases where you have to flip things because you're trying to convert numbers in the numerator and the denominator. Here, all of the numbers that we're converting are on top. So if you have a number on top and you want to get rid of it, you need to put the same unit on the bottom in the next cell in the sort of stoichiometry table. I'm not sure exactly what to call it. Stoichiometry equation here, right? So if we want to get rid of grams of octane, then we're always going to put grams of octane down here. If we want to get rid of moles of octane, then moles of octane goes down here. And then the units that we want always go on top. All right, so now we've gone from moles of A, that'll get us to moles of B, because again, these units now cancel out. So we have to go from moles of B to grams of B to finish this question. And so this is going to be in some ways the reverse of what we did in the first step. So what do we need to calculate? The molar mass of carbon dioxide, yeah. So we got carbon, oxygen. Right, so 1 carbon, 2 oxygens, 12.01 is the molar mass of carbon, 16.00 is the molar mass of oxygen. So 12.01 plus 16.0 times 2 is going to be 44.01 grams per mole CO2. So because we want to get rid of moles of CO2, we'll put 1 mole CO2 in the denominator, and then we'll put 44.01 grams of CO2 in the numerator. So moles of CO2 cancels with moles of CO2, and we're left with grams of CO2, which is what we're looking for, or what the question's asking for. Now, when you're doing the math for these, right, because we haven't actually done any math until now, or any calculations, you multiply across the top. So multiply everything on top, and then divide by everything on the bottom. So let's see, do I have space to do this? If we zoom in, so we're going to start with, this is the calculator input here, is going to be 5.0 e to the 2. This is exactly what you'll type into your calculator, times 16 times 44.01 divided by 114.26 divided by 2. All right, so multiply this by this by this, and then divide by 114.26 and divide by again 2. And so with order of operations and everything, this will come out to the correct answer. So when I say multiply by everything on top, divide by everything on the bottom, I mean that in the most literal sense. So 5.0 e to the 2 times 16 times 44.01 divided by 114.26 divided by 2. Oops. And that equals 1.54. I should just have 2 sig figs. Oh, it's just 2 sig figs. 1.5 times 10 to the 3 grams of CO2. So it'll also be the answer from there. So I know that, especially me trying to cram everything in on a single slide, and in the spaces that I've allowed on a single slide, it looks and probably feels complicated, and that's fine. But remember, you got to break things down into chunks. So the big thing is that we're doing this pretty much every single time. Grams to moles, moles to grams. And all of the mass that's on this slide for the most part, right, this is calculating the conversion factor that we needed for this first step. And the reason we have to calculate it is because we have to calculate it for every compound that we use based on stuff on the periodic table. So that information you have, just kind of have to put it together. Up here then, we found the ratio using the balanced chemical equation to get from moles of A to moles of B. In this case, octane to CO2. And then this last part was just calculating the conversion factor from moles of B, or CO2, to grams of B, CO2. And then we're plugging all of that into this large equation. So there's little pieces that aren't super hard to find. And if you can think about them as these individual chunks and work on it sort of one step at a time, rather than trying to attack the whole problem in your head all at once, again, simplify this crazy looking thing. So of course, not the only example we're going to do, but that's the idea. Are there any questions so far? All right, it's using stuff, all the stuff that we've been building up to for the past like 7 chapters. Okay, so what mass of octane would be needed? This is in some ways asking the question a little bit backwards, but what mass of octane would be needed to generate 42.3 grams of water? So what are we given? Water, yeah. So the given here is 42.3 grams of water. And what are we trying to find? Mass of octane. So mass, again, meaning grams of C8H18. So we want to start this all off with what we're given, so our grams of A. Grams of A being what we're given. So we'll put that in here and say 42.3 grams of H2O. And then we're going to have some multi-step process, right, to get all the way over to grams of B. But what is our first step? Find the molar mass of water. Yeah, because we need the molar mass of water to go from grams of A to moles of A. So molar mass of water is going to be hydrogens and oxygens. And there's 2 hydrogens, 1 oxygen. And these numbers, oh, and again, I'm rounding these to 2 sig figs to make sure things don't take up too much space because I'm already really bad at trying to keep it in this space. But normally you would just look these up on the periodic table, use the number that's on the periodic table. These ones I happen to have memorized. Right. So this is going to be 2.02, 16.00. So we're going to have 18.02 grams per mole H2O. So now how do I insert that conversion factor into the equation here? Yeah. Moles the grams of water goes on the bottom. So 18.02 grams of water on the bottom. And 1 mole of water on top. And the reason, just to reiterate this, the reason that grams goes on the bottom is because grams is what we have in the previous step. So by putting it on the bottom, those units cancel out and give us the new units that we put on top. Cool, so now we've got moles of water. What's our next step? Find the ratio. And what is that ratio? Octane what?
Octane and water, so 2 and 8.
Yeah, octane and water. And it is just the coefficients. So 2 octanes to 18 waters.
Or would we do 1 and 9?
You could do 1 and 9. Both are valid. Both will get you the same thing. So the reason you could do 1 and 9 right is because you can divide 18 by 2. I'm going to go with 2 and 18. But yes, both work. So 2 moles of octane, 18 moles water. And again, right? How do we use this in this next step of the equation? What goes on top, what goes on bottom?
Octane goes on top and water goes below.
Yeah. 18 moles H2O on the bottom. And again, that's because that cancels out our units. All right. And then the last step, we got to go from moles of B to grams of B. Or moles of octane to grams of octane. Someone new? Find the molar mass of octane, which, fortunately, we've already done. That's up here. So we can take that 114.26 grams per mole of octane. So it's going to be 114.26 grams of octane for 1 mole of octane. And that's our last step, right? Because now our units match what the answer or the question is asking for. So we multiply everything across the top. So 42.3 times 2 times 114.26 divided by 18.02 divided by 18. And we're going to have 29.8 grams of octane. So if we react 29.8 grams of octane, that will produce 42.3 grams of water. We could do this for every single part of this reaction. If we know, and I think for me this is the really cool part of like stoichiometry, because all of these things are linked together, right? We need oxygen, a certain amount of oxygen to react with a certain amount of octane, and that's always going to produce the same ratio of carbon dioxide and water. So if we know actually this 42.3 grams of water gets produced, we could calculate how much CO2 also gets produced. Or we could calculate, like we did, how much octane we need, and we can calculate how much oxygen we need. So for these problems, if you want to do extra practice, you can set up this same type of problem and just change what B is. And it can be anything in the chemical reaction. Because we have all the ratios, so we can always convert from moles of A to moles of B. And we have every molar mass, because we have the periodic table and it's got all the elements on it. We know how to add all of those up together to get molar masses for molecules. Cool. So, moving on. How did I get a marker over there? Well, that's actually on my screen. Okay, so magnesium hydroxide is the active ingredient of milk of magnesia, which neutralizes stomach acid, primarily hydrochloric acid, according to the following reaction. So how much hydrochloric acid in grams can be neutralized by 5.50 grams of magnesium hydroxide? So our given, yeah, or magnesium hydroxide, but yes. 5.5 grams of MgOH2. And what are we trying to find? Mm-hmm. How many grams of hydrochloric acid? Yep, the mass in grams. All right. Now this problem becomes the same as the previous problem. We've just changed what A is and we've changed what B is, and we've gotten ourselves a new chemical equation.
So we'll start, like always, with what we're given, 5.5 grams of magnesium hydroxide. Move this over here. So first step. Yep, molar mass, so we can convert grams to moles. So we have magnesium, oxygen, and hydrogen. We have one magnesium. How many oxygens do we have? Two. Because the parentheses here with the 2 subscript on the outside tells us that we have 2 of everything inside the parentheses. So 2 oxygens and 2 hydrogens. Magnesium is 24.31. Oxygen is 16.00. Hydrogen is 1.01. 24.31, 32.00, and 2.02. Add those together. So that's going to be 58.33 grams per mole. And how do I place that? The 58.33, that's grams of magnesium hydroxide. And that is equal to, or the mass of, what, 1 mole of magnesium hydroxide. Cool. Next step. Got to go from moles of A to moles of B. We will need the mass of hydrochloric acid, but not for this step. The ratio. Yeah, so the ratio between what we have, so magnesium hydroxide, and the hydrochloric acid. So 1 mole of magnesium hydroxide. Got to remember this is, if it helps and you get a chemical equation, you can write the ones in. That helps you remember that there is a 1 there. So 1 mole of magnesium hydroxide will react with 2 moles of hydrochloric acid. So 1 mole magnesium hydroxide, reacts with 2 moles of hydrochloric acid. So take a step back from just doing the math here for thinking about what's actually happening in this chemical reaction is that every one of these magnesium hydroxides has 2 OH molecules, hydroxide molecules, and so those can each react with 1 hydrochloric acid. So we're kind of getting a double action, right? 1 magnesium hydroxide reacts with twice as much hydrochloric acid. And that's why we see this ratio. So now we need the molar mass of hydrochloric acid. So hydrogen, chlorine, and we just have 1 hydrogen and 1 chlorine. Hydrogen is again 1.01, chlorine is 35.45. Double check that, yep. So if we add those together, it's going to be 36.46 grams per mole. And now how do I place that one so that we can end up with grams? On top. And then 1 mole of HCl on the bottom. Cool, so now we just multiply everything on top, divide by everything on the bottom. So 5.5 times 2 times 36.46 divided by 58.33. Oh yeah, just 58.33 is being divided. So I'm going to move this up here. This is going to be 6.8, sorry, 2 sig figs, 6.9 grams of HCl. Times it. Whew. Time flies when you're doing stoichiometry. So this structure of the problem really does just carry out. And it's just about finding what you're starting with, finding what you're trying to find, and then calculating each of your conversion factors. All right, so one component of acid rain is sulfuric acid, which forms when sulfur dioxide, a pollutant, reacts with oxygen in rainwater according to the following reaction. Assuming that there's more than enough oxygen and water, how much sulfuric acid in kilograms forms from 2.6 times 10 to the 3 kilograms of sulfur dioxide? Just an extra layer of complexity. So now we've kind of added another step to our overall reaction or solution diagram. Because we've been given, well, what have we been given? Yeah. Been given 2.6 times 10 to the 3 kilograms of sulfur dioxide. And we want to find H2SO4 in kilograms. So find kilograms of H2SO4. So what we can do is we can take our solution diagram and we can just add a step on the beginning, take that kilograms of A and convert it into grams of A, because we need it to be in grams because our molar masses are in grams per mole. And then at the end, we can take grams of B and add a step to convert it to kilograms of B. So if we take our given 2.6 times 10 to the 3 kilograms sulfur dioxide, how do we convert that from kilograms to grams? Yes. So kilograms on the bottom, grams on top. How many grams are in a kilogram? What? 1,000, yeah. 1,000 grams is 1 kilogram. So if we have 1,000 grams for 1 kilogram, that'll now be, I guess I could write this as SO2. And so 1 kilogram of SO2 is going to be 1,000 grams of SO2. Now we have grams of SO2, so we can calculate the molar mass to go from grams to moles. So we have sulfur, and oxygen. Sulfur is 32.07. So we have 1 sulfur times 32.07, and we have 2 oxygens times 16. So 32.07 plus 2 times 16. It's going to be 64.07 grams per mole. And so we'll put that 64.07 on the bottom. And we'll put 1 mole SO2 on top. This is the part that frequently trips people up, but it doesn't have to. It's the same as all the other problems that we've done. All right, we need to find the ratio between what we have, or given, and what we're trying to find from the balanced chemical equation. So what's the ratio between SO2 and H2SO4? 2 and 2. So 2 moles SO2, 2 moles H2SO4. Now we have moles of H2SO4. So we need to do what next? Yes, mole B to GB. Moles of B to grams of B, and again using molar mass. So hydrogen, sulfur, oxygen. There's 2 hydrogens, 1 sulfur, and 4 oxygens. 1.01, 32.07, 16.00. And so we're going to do 2 times 1.01 plus 32.07 plus 4 times 16. It's going to be 98.09 grams per mole. So put the 98.09 grams of H2SO4 on top. And the 1 mole of H2SO4 on the bottom. One last step. Convert it into kilograms. So the grams on top or bottom? Bottom. All right, so we used this conversion factor already. So 1,000 grams is 1 kilogram. I guess I could do this H2SO4, H2SO4. So it's long, but the longest part of doing a stoichiometry problem is really finding the conversion factors and calculating those conversion factors. And they're either going to come from the balanced chemical equation, the periodic table, or if you have to do something like grams to kilograms. Now there is something nice about this. So because we have, because we started with kilograms, and so we'll multiply by 1,000 here at the beginning, and at the very end, we'll divide by 1,000. Those cancel each other out. So they need to be in here because it shows which units we're converting to and from. But in your calculator, if you leave both of them out, you don't have to do them. Yeah. I was just about to say, you can also do that with the 2 moles to 2 moles. So,
Put things in the calculator that aren't canceled out?
you can do both. And I would actually say, like, come back to this and try it both ways to prove to yourself that it does work out. Because you could even type in all the ones in your calculator. It's not going to change the answer. So you do 2.6 times 10 to the 3 times 98.09 divided by 64.07. And so that's going to be 3 point, let's just do sig figs. 4.0 times 10 to the 3 kilograms of H2SO4. So there I left out all of those extra numbers, but I'll just go ahead and type it in. 2.6 e to the 3 times 1,000 times 2 times 98.09 divided by 64.07 divided by 2 divided by 1,000. And I get exactly the same number. So I think that it's safer to type in all the numbers
just in case, for whatever reason, you think, oh, I'm going to cancel these ones out, and then you go to type it in, and then you leave one of them in but not the other, and you end up with the wrong answer. So it's safer to just type everything in, unless you're really comfortable with identifying those things, canceling them, and then leaving them out of your calculator. Cool, so that is stoichiometry. That's why we spent so much time on unit analysis, because we're going to continue to do this for everything. Well, chapters 9 and 10, or 9, 10, 11, and 12, we kind of like make a little detour, and then we'll come back. All right, so in this problem, it specifically said, assuming that there's more than enough oxygen and water. So the question is, what if there's not? And that becomes a slightly different type of problem called a limiting reagent problem, or limiting reactant problem. Reagents, reactants are both sort of synonymous. So, and this is what I hinted at the beginning. So if we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder, those are all the materials that we have. How many pancakes can we actually make? So there's sort of 2 ways to think about this. You can kind of look at each of them, look at the recipe, and in some ways intuitively figure out, oh, we're going to run out of this or we're going to run out of that. You can also just set up a problem where we say, oh, I'll just calculate for each of these. And when I calculate it, I'm going to assume I have 3 cups of flour. If I assume I have enough of everything else, how many pancakes could I make with 3 cups of flour? So that's going to look like, actually, I think it's on the next slide. Yeah, okay. Yeah, we can just go to the next slide. Or no, I'll set up the problems. So it's going to be 3 cups of flour. Wow. 3 cups of flour. And then again, we can set this up because it's like a stoichiometry problem. This is like doing the moles to moles step in a stoichiometry problem. So if we have 3 cups of flour, we know we need only 1 cup of flour to make 5 pancakes. So if we say 1 cup of flour will be 5 pancakes, that'll give us 15 pancakes. Right? And that's assuming that we have enough of all the other stuff. And so then we set up another problem. We say, well, okay, maybe it's eggs that we have, or eggs is the limiting. So we can set up another problem where we say, okay, for our 10 eggs, right, again, setting up like a stoichiometry problem. And that's 2 eggs will give us 5 pancakes. So 10 times 50, or 10 times 5 is 50. Divide that by 2. So that would make 25 pancakes. But we already know with the amount of flour that we have, we can only make 15. So we have more than enough eggs, right? We have more eggs here than we can even use. And we can also do this for baking powder and say we got 4 teaspoons of baking powder. And another stoichiometry problem. So for every half a teaspoon of baking powder, we can make 5 pancakes. So this gets a little bit weirder in terms of the math, right? We don't have fractions in chemical equations, but we can do 4 times 5, divide that by a half. And so that's going to make, that's enough baking powder to make 40 pancakes. So what's our limiting reactant? It's our flour, right? We only have enough flour to make 15 pancakes. So we can't make 25 pancakes, we'd run out of flour. We can't make 40 pancakes because we'd run out of flour and eggs.
So this is going to be our limiting. And of course, the same thing applies to chemistry. If we're given quantities of all the reactants, right, masses of all the reactants, we can calculate how much of a product that we would make, and the one that makes the smallest amount is the one we're going to run out of first. So, right, if this is a chemical reaction, the flour would be our limiting reactant because we can only make 15 pancakes with the amount of flour that we have. So our theoretical yield then, in theory, the maximum number of pancakes we can make is those 15 with the 3 cups of flour. But of course, we know, I mean, maybe you're a perfect chef. I am not. So what happens though if you drop some or you burn them? So suppose we cook our pancakes, we burn 3 of them, and 1 of them falls on the floor. So even though we had enough flour to, in theory, make 15 pancakes, assuming we didn't burn or drop any of them, we only ended up with 11. So in the terms of a chemical reaction, 11 would be our actual yield. Most of the time in chemistry, it has more to do with other factors in a chemical reaction that determines your yield. Sometimes it is operator error or chemist error, making mistakes. I've personally been there. So 11 pancakes would be our actual yield. And I think it's, yeah. So using that actual yield and our theoretical yield, so on top here is the actual, and on the bottom is the theoretical, we can calculate a percent yield. And so this is telling us what percentage of the possible pancakes we were actually able to make. So in this case, it was only 73% of the pancakes. Let's see. Yeah. So the actual yield of any chemical reaction is going to be determined by actually doing the experiment. You can't determine beforehand necessarily how much or how good your yield is going to be. You have to do it. So to put this in sort of like the context of an exam, you can't calculate a percent yield unless I give you the actual yield. You can calculate the theoretical yield, but you can't calculate the actual yield. So almost always going to be less than 100%. And it's either going to be because some of the product doesn't form or because it gets lost in some part of the recovery process. All right, so like when you guys did the copper cycle lab, probably lost, I think actually everybody lost some of it to the decanting step where you have like the black fluffy stuff and you're trying to pour the water off, right? That was some of it lost, and that changed your percent yield that you calculated at the end. Let's see, what's the summary slide? Yeah, I'm going to give you a slightly different summary first. So these 3 things, limiting reactant, theoretical yield, and percent yield, are all tied together. You use the limiting reactant, and that helps you find or tells you what your theoretical yield is. And then if you have been given an actual yield, you use the theoretical yield to calculate your percent yield. So you have to get a limiting reactant to calculate a theoretical yield, to calculate percent yield. So all of those are related and are going to involve doing stoichiometry. So your limiting reactant or limiting reagent, right, is the one that's completely consumed. It's what you run out of. And it's also, or you can identify it because it makes the least amount of product. Your theoretical yield, right, that's the amount that can be made,
based on your limiting reactant, all in theory, assuming you use up all of it. Actual yield is what you have to be given or what you get from doing an experiment. And then you can calculate a percent yield with that actual yield and the theoretical yield. Let's see. What time is it? All right, we got time for like one more. Yeah, this is the next problem. Okay, so right, we did this with pancakes, but to do it with a chemical reaction, if we're asked for the limiting reactant and the theoretical yield, if we start this titanium and chlorine reaction with 1.8 moles of titanium and 3.2 moles of chlorine, right, what is our limiting reactant? What is our theoretical yield? So we'll use stoichiometry, like I set up for you in the pancake problem, to figure out the amount of the product, titanium chloride, that we can make from each reactant. And then our limiting reactant is the one that makes the smaller amount, because it's the one that runs out first. All right, so easier problem because we're starting out with moles of each. So we can start off with 1.8 moles of titanium. And we need to calculate the amount of a product that we can make here. So with our 1.8 moles of titanium, I guess I should say, what is the ratio from titanium to titanium chloride? One to, that would be titanium to chloride. Yeah, titanium chloride, 1 to 1. 1 mole of titanium will give us 1 mole of titanium chloride. So that's going to be 1.8 moles of titanium chloride. So then we do another one. We start with 3.2 moles of chlorine. And then we use the ratio from chlorine to titanium chloride. Right, so 2 moles of chlorine will give us 1 mole of titanium chloride. So 2 moles chlorine, 1 mole titanium chloride. Nice straight line. So we take our 3.2 and divide it by 2. And that'll give us 1.6 moles of titanium chloride. So even though the number of moles that we started out with of titanium was less, because of the ratios and the stoichiometry, we actually make less titanium chloride with the 3.2 moles of chlorine. So this is our limiting reactant, or chlorine is our limiting reactant. And our theoretical yield is going to be that amount that we could make with the limiting reactant. And that is always the case. So the one that makes a smaller amount is your limiting reactant. The amount that that smaller amount makes is your theoretical yield, always. Right. Cool. We'll leave it there. We can come back to that next week.